The next application of derivatives we're going to look for is something that in some ways can hardly be considered an application of derivatives and the derivative calculus at all, because it in fact was developed alongside derivatives and provided a lot of the motivation for why we do calculus the way we do. So we are going to be looking at motion along a straight line, which is essentially a lot of what you do in the mechanics part of Physics 11. So we are going to represent our variables. So x was usually used to describe position, v to describe velocity, and a to describe acceleration. And we consider these to be vector quantities, which means that sign matters, and all of these values can be positive or negative. Okay, which differentiates them from distance, speed, and acceleration taken as a scalar, which is just how fast you're accelerating, not with any respect to what direction you are going. So x, position, is the place or location where an object is at time t, and we usually use t to represent time here. Okay, so we would say x of t is the position at time t. Okay, so displacement, another word that is good to know, is how much it is moved. Okay, so the displacement is delta x, and that is the change in position from t1 to t2. Okay. And so we have to think about these things. It's just how far it's gone from T1 to T2. Okay, so now we want to look at speed and velocity. Okay, so average speed, okay, is total distance divided by total time, and it is a scalar. So to calculate average speed, it shouldn't matter whether you're going forwards or backwards. If you're going, you still have a speed. If you're going 20 kilometers per hour forwards, you're still going the same speed as if you were going 20 kilometers per hour backwards. Your velocity would not be the same. So your average velocity, okay, is your total displacement over total time. Okay, and this is the same as the slope of the secant line between the points at time 1 and time 2. So your velocity, your average velocity, is the change in your position divided by your change in time. So it's just where you ended up at the end minus where you ended up at where you started, divided by the change in time. Okay. Your instantaneous velocity is your velocity at a particular time. And this v is the limit as delta t approaches 0 of delta x over delta t. We want the tangent, it's the line that's tangent to your position graph. So that is equal to dx dt at t equals the instant you're talking about. Okay, so let's take a look at a fairly simple position versus time graph. So we have example number 1. Okay, so we have a graph, and we're going to let our time go from 1 to 4. This is our t. 1, 2, 3, 4. Let our position also go from 1, 2, 3, 4. Okay, so this is our position in meters along the graph, and this is our time. Okay, so we'll call this position. Okay, so let's have point A, time A, which is starting, let's actually start our time A at 0. We're going to start at position 1. We are going to go up to a maximum here at 3, and then we are going to go back down to position 1 by 4. Okay. So let's look at our scalar versus vector quantities. So we have A, our distance, which is just how far. Well, we have to look at distance that's increasing or going up separately from distance that's decreasing or going down. So our distance from A to B, okay? Well, from 1 to 3, we travel 3 meters in one direction, and then from 3 to 4, we travel 3 meters in the other direction. So the total distance we have is 3 meters in one direction plus 3 meters in the other direction, which is 6 meters. Our total displacement from A to B is 0 meters. Why? Because we ended up in the same place we started. We haven't actually, the change in x over, we haven't actually changed our x. We've moved, but we came back to the place we started. Our average speed, so speed is the absolute value of your velocity. It's just the positive, how fast you're going without respect to what direction you're going. So our total distance is the total distance over the total time. So we had 6 meters. We traveled 6 meters over 4 seconds. So that gives us an average speed of 1.5 meters per second. Our average velocity from A to B is 0 meters per second, because we didn't move. We have an average velocity of one thing from one place. We have a different average velocity elsewhere. So our total distance, our total displacement over our total time. And our instantaneous velocity at 2 seconds. So if we look at 2 seconds, we have a line. We've gone 1, 1, 2, 3 up and 1, 2, 3 over. So it's the instantaneous velocity. Since it's a linear relationship here, it's just the slope of the line. We don't have to try to draw a tangent line or take a derivative. The slope of the line is 3 meters over 3 seconds, which is 1 meter per second. Okay. So adding acceleration in here. Average acceleration we have our average acceleration is the change in velocity over the change in time, which is the slope of the secant for a velocity time graph. And in these graphs, time is always going to be on your x-axis. It's going to be your independent variable. So our instantaneous acceleration is going to be equal to dv dt, okay, which is the derivative of dx dt, because we said that our velocity was the derivative of our position graph, which is equal to d2x dt squared, which is our second derivative. So it's the second derivative of the position graph. Okay? So let's take a look, okay, at what we want. We want to think about what's happening on a graph. So let's take a look at a position time graph and think about what's happening with respect to our first and second derivatives of our position and time graph. So if we have here a graph, this is example 2. Okay, so this is our x, our position graph. Okay, this is t, our time axis. Okay, so let's draw a nice curve that represents the position of our particle. We often use a particle when we're talking about these graphs. Okay. And then let's talk about what this position graph means in terms of what we understand about the first and second derivative. So remember, x prime is v, gives us v, and v prime gives us a. X double prime gives us a. Okay, so what's happening here? We have a graph and we have a point up here. We have 2 critical points. So that means the derivative of this graph is 0. So what this means is v equals 0 here and here. So this is a momentary pause. So stops. Our particle stops momentarily at these points. Okay, so that's what's happening at these max and min. Stops momentarily. Okay, so let's look at what is happening along this graph. So for the first part, we are going up. So we are an increasing function. Our velocity is our derivative of the velocity is the derivative of the position graph. So since the velocity is the derivative, we have a positive velocity. So here we have a v plus in this piece of our graph. And we have acceleration. We are concave down. So since we're concave down, we have a negative acceleration. So if the velocity is positive and the acceleration is negative, it means we are slowing down. Here we start to be a decreasing function, but we're still concave down, which means we have a negative velocity. We're going in the opposite direction than we were going. And our acceleration is also negative, so that means we're speeding up. Okay, but we're speeding up in the opposite direction. And now here we have acceleration equals 0. And this is again momentarily. This is our point of inflection. And what that means is basically you're coasting. You're going at the same speed just for a second without accelerating. Okay, now we switch concavity. So we are going into a region where our velocity, we're decreasing, so our velocity is negative. So decreasing position, negative velocity. Acceleration, we are concave up, so our acceleration is positive. So if we're going in a negative velocity, we're going backwards, but we're accelerating in the positive direction, that means we're slowing down. And so here we can see our v equals 0. Okay, we stop again momentarily, except this time we were heading in the other direction. Now we are going concave, we are going up, we're increasing, so that means velocity is positive. Here we are also concave up, so that means acceleration is positive, so that means we're speeding up again. So if you look here and here, these 2 situations, right here and right here, mean we are slowing down. And when we're slowing down, okay, velocity, our acceleration is in the opposite direction of velocity. So slowing down means not the velocity, but the speed is decreasing. Okay, Slowing down, our speed is decreasing. When we're getting ready to turn around, when we have this situation here, velocity minus, or velocity plus, okay, sorry, let me get that blue color in here. These are slowing down situations. And these right here, our yellow ones, are speeding up. Okay, so speed is increasing in whichever direction you are going. Okay, so these are slowing down, speeding up, but we can't confuse that with the velocity changing. So acceleration is negative means the velocity is decreasing. That makes sense. Acceleration is the derivative of the velocity. When the derivative is negative, the function is decreasing. Acceleration is positive you have your velocity increasing. And one of the hardest times I think people have with physics questions in general when we're applying calculus to them is just understanding the physics, which is the difference between what velocity is, which is sign matters, and what speed is. And in speed, the sign doesn't matter. So you can be speeding up and moving faster in a certain direction. It depends on whether the acceleration matches the direction you're going, not whether the acceleration is positive, because positive acceleration is accelerating you in a particular direction. Accelerating backwards from the direction you're going is actually going to serve to slow you down. Okay, let's look at an example problem where we have to apply this idea of velocity versus speed. Okay, a lot of answering these physics questions is just trying to determine what they're asking you in terms of what are you looking for positive, what are you looking for negative, what different regions are you looking at. And it actually can be really similar to curve sketching, some of the questions you're asking. So the position of a particle is defined by x at t equals 4t cubed minus 6t squared. Okay, so question A is when is the particle moving forward? Okay, so the first thing to do is what is this asking? So we're asking when the particle is moving forward. What this question is really asking is it's asking us about what direction it's moving in. And so the direction it's moving in is determined by so when is the position going to be going up? So the position is going to be increasing, it's going to be moving forward or further along the line. So when is the velocity, the slope, positive? Okay, so we're looking for increasing position, positive slope, positive velocity. Okay, so velocity has to be positive. So we want to look for what regions the velocity is positive on. Really, we're just figuring out at what regions graph is increasing. Okay, so let's look at our velocity. V of t is dx dt, which is 12t squared minus 12t. And we want to know when this is positive. So we want to know when is 12t times t minus 1 greater than 0. We want to know when it is increasing. So whenever it's greater than 0, it is increasing. Okay, so I like to solve these problems by drawing a parabola. You can also solve them by making a sign chart. That is up to you. Okay, so we have roots here at 0 and 1. So 0, 1. So that means those are the places where we are going to pause momentarily and potentially switch the direction our velocity is going. Okay? Nothing before time equals 0 makes sense because this is physics, so we are going to start right at 0, but we can think about what this parabola looks like outside of 0. So we'll draw a dotted before 0. This is an upward opening parabola. Here we actually have a parabola. So we're going to be negative between 1 and 0, and we're going to be positive after 1. So the particle is moving forward. Apparently my OneNote is also moving forward. The particle is moving forward when t is greater than 1, and we can add and t less than 0 if for some reason we're allowing times less than 0. So before the starting point, if the particle was moving before we started measuring it. Okay, so next question. When is the speed decreasing? So we're asking when the speed is decreasing. So we're asking when is the velocity positive and the acceleration negative. So when are we going forward but we're accelerating backwards? That means we're slowing down and moving forward. Or when is the velocity negative and the acceleration positive? When are we going backwards but slowing down, starting to go accelerating back towards the positive? Okay, so we know when the velocity is positive. We now need to figure out when the acceleration. We know when the velocity changes from being positive to negative at 0 and at 1. We don't know yet when the acceleration changes. So let's figure it out. So a of t is v prime of t. So we can just take the derivative of our velocity, which is equal to 24t minus 12. If I plug in 0, we're going to look on both sides of the 0. I get 24. I get 0 is 24t minus 12. And we get t equals 1/2. So I can go, and I'm looking for regions. What I'm going to do is I'm going to construct something that's fairly similar to what my tool I use for curve sketching. As I said, we have 0, 1/2, and 1. We're going to look at our velocity. We're going to look at our acceleration and where it's positive or negative. From the last part, I know velocity is positive here. It's negative both places between 0 and 1, and it's positive when it's greater than 1. Acceleration is negative before it gets to 0, because if we pick a negative number, negative 24 minus 12, negative. It's negative between 0 and 1/2, negative, plug in 0. And as we get greater than 1/2, if we plug in, say, 1, it's going to be positive. So it's once we pass 1/2, we start getting positive. So we're looking for speed decreasing means velocity and acceleration have opposite signs. Acceleration have opposite signs. Okay, so we're looking here, plus minus, and here, minus plus. So when we're answering the question, we can say the speed is decreasing when t is less than 0. I'm going to put that in brackets just in case we're allowed to think about what's happening at times before we started measuring. And when t is between 1/2 and 1. Okay? The speed isn't, when the speed is 0, the speed is not decreasing. The speed is 0.